Okay, for our senior design 2 project, we made an electromagnetic ferrofluid display. We are group 4, which includes me, Jacob Willie, Gavin Starnes, Brock Franklin, and Timothy Terry. This project is to create a small display which uses magnetic fluid in combination with an array of magnets to project images onto a display. The fluidness of the display creates a visually pleasing experience that cannot be replicated with anything else. The seemingly magical movement of the fluid is visually appealing and a great talking piece. Magnetic fluid is a substance called ferrofluid. Ferrofluid is a liquid that has ferromagnetic particles suspended in a carrier fluid. It was originally invented by NASA in 1963 to create rocket fuel that could be controlled in a zero-gravity environment. The project shows the use of a non-conventional display that can show differing designs specified by code. The possibilities of the display are limited only by software development. The design can support many functions such as an abstract art piece, a display for information, or a display for interactive games. The display works much like a rudimentary pixel display of sorts. As the project stayed active, the display would move between several sets of predetermined display formations within the 5x10 grid format made by the electromagnets. The ferrofluid will be suspended in a glass tank that was filled with supersaturated salt water. The ferrofluid is suspended in the solution in a manner to give it the appearance of being in a state of zero gravity. Cycling through the magnets can create organic shapes and movements appealing to the eye. This is similar to a lava lamp, but does not require any heat, which is much safer and is more adaptable, more programmable. So here we have a picture of the electromagnetic array, which is on a piece of plexiglass, and the wires go through the glass. Here's some more pictures of the same display. You can see how the wires go through the glass here. So our original design used a plexiglass container. We used acetone to weld the pieces together, and we held the pieces together with the clamps as shown in this picture. This is our original design, original theory, and we ended up having issues with this, but this is what we originally did. The issues with the last one was the plexiglass seemed to cause staining with the ferrofluid. And it was harder to clean also. But our theory was that plexiglass was the issue because of many experiments we made. So we moved to a glass case, which is seen here. This uses glass instead of plexiglass.
This is the PCB we designed for the power delivery and signal propagation of the board to the magnets. Initially, we used a TIVA microcontroller that was controlling the PWM chip on the board, which would activate and actuate the MOSFETs that would drive the magnets. However, due to some issues that would later be changed, this is the I2C bus on the oscilloscope that was used. This is the signal that would tell the magnets which ones to turn on into the PWM controller. And this is micro soldering of the PWM controller onto the control boards. This is the ferrofluid display with it being prototyped with the I2C control. Here's a short clip of it moving a screw between the magnets with control from the I2C. Here's a video of it doing the same thing with the PWM controller, but with the actual ferrofluid. This is the final prototype we ended up with, where as I mentioned earlier, we had to change out the TIVA and the PWM controllers for an Arduino, as there was an issue with the PWM controllers causing them to no longer work.
As you've shown here by our block diagram, the power supply is fed directly into our driver boards of the PCB or the PCBs, and the PCBs receive signal from the Arduino microcontroller that tells which pin or which magnets to activate and deactivate to pull our ferrofluid up, down, left, or right as we see fit.
So on the driver boards, we are using power MOSFETs, and the Arduino microcontroller has digital outputs for each magnet. Each magnet is controlled by one MOSFET, and the digital outputs turn on the MOSFETs. And the Arduino is hooked up to the laptop, which is just USB power. And the Arduino IDE is the code that's running on the microcontroller. This is the program we wrote, which has some preset things for the magnets to do, preset designs. So yeah, driver board connects to the magnet array.
This is a more physical showing of the flow chart of the block diagram. As you can see, our code is connected directly to the Arduino board, and the MOSFET arrays are connected directly to the magnet array to give us our outputs.
So here's a flow chart of how our program works with Arduino. First, we're going to choose a function or a task to be completed. So this would be the design that you want the magnets to do. Once you've chosen that, you can start the program. The program will turn a certain magnet on. Then it will, the program will, you'll tell the program it needs to turn a magnet on. Program will ask, where is the magnet? Do we need to turn it on directly, or do we need to get fluid from the bottom of the display first? If we just need to turn the magnet on, we'll turn it on. If we need to get fluid from the bottom or get fluid from an adjacent magnet, we'll do that. So then we'll transition from either the bottom magnet under it, from the bottom of the display to that magnet, or transition from a magnet adjacent to the magnet that you're turning on. And then you go back up and ask, do we need to turn another magnet on? And if we do, we repeat this process. If not, then we will stop the program.
This is our circuit diagram for our PCB layouts. As you can see, the external output of our power source is connected directly to a pull-down resistor diagram to avoid feedback. It feeds directly into the MOSFETs that then give appropriate signals to the output, which would be our This is our
a diagram of our tests. We tested how quickly we could switch between magnets and it would still pull the fluid. And so here we see some of the refresh rates, and an X represents a successful movement of the fluid between magnets.
So we have the code for holding the magnets and the code for switching. And they're both in seconds. So when we're making a transition between two magnets, the holding section is how long the magnet stays on. And then the switching would be how long both magnets are on while switching between them. So the magnet that you're transitioning to that is on turns on, and then the old magnet turns off. So from the test, we did 3 tests for each speed, and if it failed, we assumed that it wouldn't be viable. So we did these tests, and as you can see, the best test was test 5. That was our fastest test to be successful. Well, at test 5 was the fastest originally. When we got to test 8, we changed some chemical properties. We changed the density of our saltwater solution. This allowed the ferrofluid to suspend itself neutrally. And when we did this, we can see that test 9 was able to go a lot much faster and still be successful. So the way we measured the success of this test is this test was moving a blob of ferrofluid between 7 magnets, and it was a success if it went from magnet 0 all the way to magnet 7 without losing any ferrofluid.
This is a chart of all our costs for all the materials of the project. This includes some of the materials that were not included in the final design, such as the materials for our earlier tanks and the PWM controllers, which we ended up not using. The total was around $700, and to make it with just the parts used was around $500. We would like to thank the Clemson University Department of Electrical and Computer Engineering for providing us with the funding and support used in this project. We'd also like to thank Dr. Raza for his guidance and patience with this project.